Welcome to section 3 of the course titled Production Management. In section 3, we'll be looking at linear programming. If we can vividly recollect from our section 1 where you introduce models, where we talk about the 3 types of model, and if you can vividly recollect where I discussed model in session 1 of this course, I talked about the types of model, in which mathematical model is one of them, in which mathematical model is one of the type of models. And I said earlier then that we'll be applying mathematical model in the course of the course. So one of the mathematical model we'll be applying now is linear programming. One of the mathematical model we'll be applying is on linear programming, and at the end of this session you should be able to explain the meaning of linear programming, enumerate the assumptions of linear programming, highlight the steps in formulating linear programming problem, discuss the graphical method of solving linear programming problem, and understand some basic terms in linear programming. So let's quickly rush through the meaning of linear programming. Is a technique for choosing the best alternative from a set of feasible alternatives. A situation in which the objective function as well as the constraints can be expressed as linear mathematical function. What do we mean in essence? Is a tool. Linear programming is a tool for choosing the best alternative or the best choices among various feasible choices. That is, a manager having faced with a particular problem. Of course, in solving the problem, there should be alternatives, not only a solution to a problem. We have different or numerous solutions to a particular problem. So how does the manager knows the best solution that fits into solving the problem? That's what linear programming seeks to address. Having identified the problem, the objective, and the constraints, among the requirements of the application of the linear programming technique is that the objective function and the constraints can be expressed as linear mathematical model. That is, having an objective function and a constraint that can be expressed as linear mathematical function. If this is put in place, then the application of linear programming technique, then the application of linear programming technique is visible. So simply put, linear programming is all about choosing the best alternatives among feasible alternatives. That's what do you mean by feasible? Like I said, that this solution to a problem is what is possible, is feasible. Given that, for you now to select the best or the optimal solution that best address the identified problem. So that's the simple explanation of the linear programming technique. So you have the certain requirements for the application of linear programming technique. Although in the course of explaining linear programming, I've made mention of some of these requirements, but let me quickly brush through these requirements, and I will implore you to refer back to the notes so that you can have a deep understanding of those requirements, because I will have to brush through it. So 1, there should be an objective function. It should be clearly identified and measurable in quantitative terms. Your objective function must be clearly expressed. In the course of the expression, it must be expressed quantitatively. It must be expressed quantitatively. So what do you mean by the object? As far as linear programming is concerned, our objective can either be minimization or maximization. Is that you are minimizing or maximizing? What are we minimizing? As a manager, as a decision maker, of course, we want to maximize positivity profits, contributions, surpluses, returns, revenue, among others. And on the other hand, we also have the minimization objective. What do you want to minimize? You always minimize your losses, minimize your cost, anything, any negativity, anything that has negative effect. Achieving the objective of the organization or achieving the production of the objective, then a manager or a decision maker will do what? We always seek to minimize on such. So is that the objective? Is that you are minimizing or you are what? Or you are maximizing? So the second one is activities to be included should be distinctly identifiable and measurable in quantitative time. That is, the activities that the manager wants to carry out or the organization wants to carry out should also be identifiable and be expressed quantitatively. Then the third one is resources of the system that you want to use in achieving or realizing this identified objective must also be identifiable and measurable quantitatively. The resources of the system, the available resources at hand. So in most cases, these resources are referred to as constraints. So, and the constraints carries different signs, the inequality and the equality sign. We have the greater than equal to constraint, we have the less than equal to constraint, equality sign, and we have the equal to sign. So for having a less than equal to constraint, this implies that the upper limit of the amount of some scarce resources available for use, that is, when you have a less than equal to sign of the constraint, it means that you have that's the maximum unit or maximum value of what? Of the resources you have at hand. On the other hand, the greater than equals to sign implies what? That the minimum, that is the minimum outcome or output as far as the optimal solution is concerned. While for the equal to constraints, that's the exact, that is when something is equal to, that means that exactly what you have, exactly unit or exactly value of such constraints. Or move further to examples, practical solutions of linear programming problem. Take you understand this constraint sign better. I hope so. Now the fourth requirement is that the objective function and the constraint equation must be in linear form. That is, this our objective, our constraints, our activities must be expressed in linear form. So that's when we can apply the linear programming technique. The next one is there should be series of feasible courses of action available to the decision maker. Having identified the resources at hand, then you must be able to identify feasible alternatives. You must not be stick to one particular alternative. No, feasible alternatives. So that is from those feasible alternatives that you now make your decision based on optimal solution. That is, one of the alternatives is going to be the optimal solution to address that particular problem. So that's that on certain requirements for application of linear programming. So we move to the next subheading, which is the assumptions of linear programming. So among the I'll just list some of the assumptions. One, we have proportionality, additivity, linearity, certainty, continuity, finite choices, mono objective. What do you mean by finite choices? As I said earlier, that you have a set of visible alternatives, and we are talking about, what do you mean by finite? Something that is limits. So limited feasible alternatives. Not that the alternatives are uncountable. No, it is even visible in the first place. You can see that yes, you can achieve this, you can achieve this, you can achieve this. So it now depends And how, when you arrive at the optimal solution, you now see that yes, let me go for A instead of going for B and C. I think A is the best solution. But when you have numerous infinite choices of alternative, then you will be lost at the end of the day. So the alternative are what? Feasible finite alternatives. Then mono objective, you can only achieve one objective at a time when you're applying linear programming. Is that you are minimizing, or you are what? Or you are maximizing. So that's that on the assumptions of linear programming problem. So we move to the next one, steps in formulating linear programming problem. So for you to formulate the linear programming problem, that there are certain steps that you must follow in order to get to formulate a real linear programming problem, such that you're able to arrive at an optimal solution. So steps, one of the first steps is you must identify your decision variables. What do you mean by decision variables? Decision variables of the problem. What do you mean by this? That is the activities of that decision maker, of the production manager. What is that decision maker into? What problem has he identified? What problem is he trying to solve? So you must identify that. That's what is called decision variables. And these decision variables can be in form of producing particular goods, rendering services, producing parts, processes, and so on. Processes among others. Having identified the decision variables, that is, as an organization, these are activities. Having identified that, the second step is you formulate the objective function to be optimized. As I've said earlier, our objective function is how you are minimizing or you are maximizing. So for that organization, or for that production manager, or for that decision maker, maybe you want to maximize profit, you want to maximize your contribution, you want to maximize revenue. So you must formulate that objective function. By formulating it means by expressing it in a linear form. Don't forget that it must be expressed in quantitative term. After being expressed in quantitative term, then you must be able to also formulate it in a linear form. So having done that, the next step is you identify the special constraints. What do you mean by the special constraints? These are the resources to achieve that particular objective that you've identified. The resources to achieve those particular objectives. So now, an organization, production department, you have machine hours, you have labor hours, you have expertise, you also have processes. Probably when you are assembling a particular product, so you're spending so hours in the machine, spending so hours with labor, and so on and so forth. It may be in form of raw materials that you want to use. It may be in form of raw materials that you want to use in the course of the production. It may be in form of machine hours. It may as well be in form of labor hours. Quantity of raw materials to be used. So this also should be expressed in linear form. So it now depends on the kind of objective that you are achieving that will indicate the type of inequality. Either you are using inequality sign or equality sign, as I've explained earlier in the requirements for application of linear programming problem. So the fourth one is the non-negativity condition. What do you mean by the non-negativity condition? That is, you can't have a negative outcome. The decision manager or the decision maker cannot make a negative decision, cannot have a negative outcome. For example, production, as far as production is concerned, the production manager cannot produce negative values of products, of goods or services. Rather, it's not the production manager is not producing anything, or is producing some quantity. So that's the brief explanation of the non-negativity, the non-constraint. Now let's look at the methods of solving linear programming. So there are two basic methods. We have the graphical method and the simplest algorithm method. As far as this class is concerned, we only focus more on the graphical method. So when you get to your maybe level 5, you'll be talking about the simplest algorithm method. So let's quickly discuss the graphical method. So the graphical method is a method of solving linear programming problem with only two unknown or decision variables. So that's just the simple definition of a graphical method. It can only be used to solve two unknowns or two decision variables. When your decision variable is above 2, when your decision variable is more than 2, then you can't use the graphical method. So then you'll be using the simplest algorithm method. So it can deal with any number of constraints, but each constraint is what is being represented by a line on the graph. So thus, the larger the number of constraints, the more difficult it becomes to read the lines on the graph. So advisable, it's better you use it for a minimal number of constraints. So if you see that the constraint is large, for simple reading, in order to avoid difficulty in reading the lines, then it's better you use the simplest algorithm method instead of the graphical method. So let's look at the steps in solving the graphical method of linear programming. So we have 4 steps as far as this is concerned, and the first one is you identify the problem. By identifying the problem, you identify the decision variable, the objective function, and the constraint functions, the constraint function as well. So having identified that, you plot the graph that include all the constraints and you identify the feasible region. Before you plot the graph, of course, before you can plot the graph, that means you must have identified your coordinates, your points on the graph, on your x-axis, on your y-axis. What value of x do you trace to y in order to get a graph at the end of the day? This must have been generated from what? From your objective function vis-a-vis your constraint function. So when we get to the practical example, you get to know of how we arrive at this. So to plot the graph and identify the feasible region. What do you mean by the feasible region? Is that region on the graph which satisfies all the constraint function. It does not contravene any of the constraint function. Don't forget that when I made mention of the inequality sign the other time, talking about the less than equal to, that means that's maximum value or that's maximum unit for that particular resources. When you talk about the greater than equals to sign, that's the minimum output as far as that resources is concerned. So all this must be put into consideration in identifying the feasible region. If you identify an area that extends beyond a particular constraint, does that satisfy that constraint? So these are things you need to know as far as identifying the feasible region is concerned. So when you identify the feasible region, you obtain the corner point on the feasible region. What do you mean by the corner point? The corner point indicates the feasible alternative choices or alternative solution to that particular problem. That is, at those points on the graph. They are feasible. Decisions are visible. Decisions are feasible at that corner point. So it's not left to that decision maker to see that feasible, to see that point that will yield the best or the optimal solution to that particular problem. So that's corner point on the graph. Then after identifying the corner point on the graph, so from there you identify from the corner point, you will see that point that's us or the optimal solution. So having identified that, then this next step is to interpret the result. So illustration of a linear programming problem. Let's look at, so here we'll be looking at 2 illustration. We're looking at the maximizing illustration, and we'll be looking at the minimizing illustration. As for the illustration, we have a problem on ground already. we are not asked to formulate this problem. The problem has been formulated already. So what we need to do is to solve the problem using graphical method. So I will explain how we arrive at the values that we use in plotting the graph. So in the second part of this session, that's where we demonstrated this on the board, so in order further or proper understanding. But here permits me to do what to explain what we have in the notes. Let me just explain how we arrive at those values. Now, the first example or illustration is a maximization case, and the problem has been formulated. We have our decision variables, we have our objective function, we have our constraint function, and we also have our non-negativity function. As for the decision variables are x1 and x2. Let's assume that here the production manager is producing x1 and at the same time producing x2. The production manager has two goods to do what? To produce. Good x1, good x2. That is the decision variables of the organization, of that decision maker. Followed by the objective function. The objective function has stipulated maximize 6x1 plus 7x2. That's the objective function. Maximize 6x1 plus 7x2. So that's our objective function. Then we have our constraint function, subject to 2x1 plus 3x2 less than equals to 12, 2x1 plus x2 less than equals to 8. So in front of it you see constraint 1, constraint 2, and constraint 1 indicates what? Our machine hour, and constraint 2 as well indicate our labor hour. Then we have the non-negativity constraint, which is x1 x2 greater than equals to 0. That is that the production of x1, production of x2, is that it equals 0 or what? Or is greater than 0. So that's the typical linear programming problem that has been formulated. Now, how do we solve? Now, from that's section, the first step of solving the graphical method, we formulated our problem. Having the problem, you don't have it from the front of it. You want to do what? You want to derive the coordinates of the graph or the points of the graph from this problem. So we move to the next stage of what? Deriving the points on the graph. So we now bring out the constraints one after the other. We let the objective function be. We now have business with the constraint. So from constraint 1, before I move to that, let me quickly explain what that problem says. The objective function says maximize 6x1 plus what? 7x2. The implication of that is for every product or good x1 produced, that means the producer is expecting a return of 7, let's say 7 naira. And for every product x2 produce or good x2 produce, the manager is expecting a return of what? A return of 7 naira. For every product 1, the manager is expecting a return of 6 naira. For every product 2, the manager is expecting a return of 7 naira. The coefficient of x1, that means at the end of the day we're able to get our x1. That means the total return the manager will be expecting from x1 will be what? 7 multiplied by the value of x1. Sorry, 6 multiplied by the value of x1. While for x2, the total return the manager will be getting from x2 is what? 7 multiplied by the value of x2. That's simply what that means. The objective function. The coefficient of x1 multiplied by x1. That's what will give you the total return for x1. So as for the constraint function, the constraint 1 says 2x1 plus 3x2 less than or equals to 12. That is, for every unit of product 1 or good x1 produced, the manager will be using 2 units of constraint 1. And what? For every unit of product 2 or good 2 produced, the manager will be using what? 3 units of constraint 1. The same thing for constraint 2. For every unit of good x1 produced, the manager will be using 2 units of constraint 2. That, don't forget, here is an hour. So 2 hours of constraint 1. But let me just put it as units. So it now depends on whatever you have that you'll be measuring. Maybe you are measuring in hours, you'll be measuring in kilos and the like. So let me just put 2 units of x1, and what? For every unit of x2 to be produced, x2 has a coefficient of 1, even though that 1 is not visible. But having x2 here means that it's 1 multiplied by x2, so it has a coefficient of 1. So a unit of labor hour, that is constraint 2, will be needed. For constraint 1, we have 2x plus 3x2 less than or equals to 12. That is, in totality, the maximum number of resources or labor hours available is what? Is 12. The maximum hour that is available is 12. So the producer cannot use above 12 hours of labor, 12 hours of machine for constraint 1. While for the second one is 8. So the producer cannot use above or beyond 8 hours of labor. So that's simply the explanation of that formulation. So by arriving at our coordinates, we do what? From our constraint 1, we bring out our constraint 1, and we assume that the whole of the constraint is used in the production of x2. We assume x1 to be 0. When you substitute for x1 to be 0 from that constraint, we equate it. We have it as an equation now, not as an inequality sign. We have it as an equation. So we equate it to 12. So when we assume that all the resources are, when we substitute x0 for 1, then we get the value of x2 to be 4. The same thing for x2. When we substitute 0 for x2, we get our x1 to be 6. So that's for constraint 1. The same thing applies for constraint 2. We assume our x1 is 0. I'll get our value for our x2 to be 8. And when we assume x2 to be 0, we get the value of x1 to be 4. So we've arrived at the coordinates. We've identified the coordinates or the points on the graph. The next thing is for us to plot the graph. So after plotting the graph, we identify the feasible region. As for maximization, because the feasible region is always in the inner part of the graph. The inner part of the graph always satisfies the constraint. So when we identify the feasible region, from the feasible region we also identify the corner point. So in this example, we have 4 corner points. And what do you mean by the corner points? That is those points on the graph that is within the feasible region, that decisions are visible, that solutions are visible. So in order to now arrive at the best solution from this feasible point, what we do is to what? Substitute the value of x1, x2 at those points in the objective function. Write out the objective function. We substitute the value of x1 and x2. We identify the value of x1 and x2 at those corner points, and we substitute those values in the objective function. So as far as this example is concerned, we have 4 corner points. Corner point A, corner point B, corner point C, corner point D. Corner point A is the origin, and at the origin, that means we have is 0. So the value of x1 and x2 is 0. That means we are having 0 objective. That means the decision at that end is that the producer is not producing anything. The producer has the choice of not producing anything or producing something. So at point A, the producer's decision is that it's not producing anything. At point B, the value of x1 is 0 and the value of x2 is 4. So at that point, that means the producer produces only x2, and that is only 4 units of x2. That's what the producer can produce given the available resources, and producing no unit of x1 at all. So at the end of the day, the contribution we have, or the return we have from production, is what? Is 28. At point C is the intersection. That point is the intersection of what? Of the two constraints. And because of the fact that we are not drawing to scale, what we do is what we do there is to solve the constraints that intersect at that point simultaneously. And don't forget, we have only two constraints, and those two constraints are those that are intersected at that point. So we solve simultaneously. When we solve simultaneously, we get the value of x1 to be 3 and the value of x2 to be 2. So that means 3 units of x1 to be produced and 2 units of x2 to be produced. They give us a total return of what? 32. Let's say 32 naira. While at point D, we have the value of x1 to be 4 while x2 to be 0. So such that there we have a return of 24. There we have a return of 24. And don't forget, by plotting your graph, is that you have it as x-axis, y-axis, y-axis, or x-axis. Anyway, it is either you're having y to be on the vertical axis, x to be on the horizontal axis, or x to be on the vertical axis, y to be on the horizontal axis. It depends on how you labeled your graph. So, but be that as it may, you're still going to arrive at the same answer. Just that the value on your corner points may be different, but you see, we are still going to arrive at the same answer. So the return we have at the 4 corner point, that is the 4 decision variables we have a return of 0 naira, we have a return of 28 naira, we have a return of 32 naira, and we as well have a return of 24 naira. So, and don't forget that we are maximizing. So what decision will the manager make from that? Of course, due to the fact that we are maximizing, the manager will go for that point that has the highest or the maximum value of return, which is what? 32 at point C. So the decision of the manager is that the production manager will be producing 3 units of x1 and 2 units of x2. That's the decision. Production manager will be producing 3 units of x1 and 2 units of x2. In order to have a maximum return of 32 naira. So that's that for the maximization problem. As for the minimization problem, we have a different problem to solve, but the same process applies. Just as in drawing you arrive at the coordinates or the points on the graph the same way we did for the maximization problem. Just that in identifying the feasible region for the minimization problem, the feasible region is always at the outer part of the graph. Don't forget, when you are talking about minimization, the greater than equals to sign implies that it can be, that's the minimum value or the minimum outcome of that resources, so it can be more than that. So that's why we always have the feasible region at the outer part of the graph. So for that example, we have 3 corner points: corner point A, corner point B, and corner point C. Corner point A, at corner point A, you identify the x and y, and a return of fire your x, y, and y at corner point A, and you substitute it in the objective function at corner point B, at corner point C as well. So the final decision is that the minimum value, let's say we are minimizing cost, the minimum value at that point is point C, where value or total cost is say 3,246. As for the minimization problem, we go the same way of the maximization problem, just that the feasible solution is located at the outer part of the graph. So although you will see all those ones in this practical illustration of the solution to the problem. So that's that about the illustration. So let's quickly move to the linear programming terms that are available. Some of the linear programming terms that are highlighted here. So we have what we call the binding and the unbinding constraints. What do you mean by the binding or non-binding? A constraint is binding when the right hand side is equals to the left hand side. That is, after arriving at the value of the decision variable. For example, the one we work x1 and x2. When we get the value of x1 and x2, after substituting the value of x1 and x2 in the constraint function, when the right hand side equals the left hand side, when the left hand side equals the right hand side, then the constraint is the binding constraint. While on the other hand, if it does not equate, is an unbinding constraint. We have the primal and duality. We have primal and duality. For duality means the inverse of a particular problem. That is the opposite of a particular problem. If a problem is minimization, then the opposite is maximization. If a problem is maximization, the opposite will be minimization. Then we also have sensitivity analysis. Sensitivity analysis is the reaction of the constraint to any change in the parameters. There may be changes in changes in the objective function, changes in the decision variable, changes in the constraint function, either in the left hand side or the right hand side of the constraint function. How does the final solution react to these changes? That's what we call the sensitivity analysis. Then we have what we call the equality and inequality. I've explained what we mean by that earlier. So with that, we come to the end of session 3. Thank you for listening.